So while we wait for the projector to work, do you have questions regarding anything that was taught last week? So the idea is going to be, as I was going to announce beforehand, that from the next frontal lesson, then we're going to start talking about exercises and training for the exam. Therefore, I don't know how on earth this is actually not working. Anyhow, the thing is going to be that. So, starting now. Okay. Not something you wanted. Why is it showing the can? So while we wait for this kind of nightmare, I'm going to use the Wi-Fi. So starting from the next frontal lecture, then we're going to discuss the exercises for the exam, and so my suggestion will be just to bring some kind of pen and because actually I'm going to provide like the text of the exercises in a piece of paper, and then otherwise I'm going to project the slides, and everything is going to be available also online, and those are going to be the same exercises that you have in Canvas. So let's do like that. Announced. Accept risk and continue. Let's do like that. Showing something, nothing at all. No, I'm not screen sharing a thing. Huh? I see that I'm on Chrome. Does it feel HDMI? Oh, thank God. So before we start discussing monitors, I just restate the obvious while I take time. Do you have questions, either related to everything that was taught or to the coursework? Okay. So if none, then let's go back to the last lecture, really. Bounded buffer. Yes. Which is actually related to semaphores, so that is actually going to be discussed now. The thing is, now they are becoming more of an historical relic rather than something used in everyday lives, due to the fact that actually achieving the same capability of a monitor as I was discussing is somehow convoluted. And so you can also use semaphores that are mainly used for whenever you do not want to think about how many resources are obtained or stopped. But actually everything that is a semaphore could also be implemented with a monitor. So just to provide intuition of what semaphores refer to, actually they refer to signaling monitor semaphores like the ones that you used like in nautics or in ships. So that is the origin of a semaphore. Then we have also the roadside unit utility that you have nowadays, but that is actually when they originated. So they were intended just to be used like visual signals for letting know the boats whether they could proceed or not. And that is going to work similarly like in the real world semaphores that you have. So when you have a red light, then you could pass, otherwise, sorry, the other way around. If you have a green light, then you can pass, and if you have like a red light, then you need to stop and wait to have like the precedence. So in there it's going to be similar. In here you're going to have just one access point. So and then the counting measure is like having like a global semaphore, like this kind of semaphores, not like nowadays where the semaphore, the roadside unit, is actually distributed across cars for simplicity. So it's like having one single resource that actually you're using for arbitrating the access to the resource. And what are those? So instead of engaging too much with theoretical details, so that's why I have this kind of slide description. And here you could say how to implement a semaphore using a monitor. Therefore, that also provides like a simplistic exercise. As I was discussing last time, then a semaphore acts as follows. So you are providing like in the constructor argument, which is the initial value or the amount of initial resources that are available. And the rationale is that is like how many processes could start and provide and continue the execution. And the rationale is that whoever wants to access the resource needs to do an acquire. So I want to acquire something, and then eventually I will need to call a release. And differently from locks, on which they are guarding like a critical section, on which is actually strictly required to first acquire the lock and then to release it. In here, you could also have that in different parts being detached, and you will see that that is merely related to the definition of a semaphore and definitely to the way you are required to use them somehow. But you are going to see that later on. So whenever you're acquiring, so you are trying to subtract the number of total resources, and then you're checking whether the variable has become less than 0, and in this occasion then you're waiting. So you see I'm using like the old school monitors just to provide a use case example for both. And then you know that whenever you're going to be notified, then you could continue the execution. Why? Because you'd have that the one releasing the resource is going to free the previous resource, and therefore is going to notify whoever was waiting that then they could continue with the execution. So you see in here, I could also have a process continuing doing releases and therefore incrementing the amount of free and available resources. So that's why they're called in Java acquire and release, because they are explicitly defining the notion of releasing a resource and acquiring it. So I also provide the old terminology of operations in there on the sites, because that comes from a paper written by Dekker, on which they used the terminology proberen for acquire and verhogen, V, for release. So you might also see that as proberen and verhogen, but you also have acquire and release, confusingly enough, or P and V respectively. So I'm just providing all the possible terminology that you might find elsewhere in other resources in here. And in here, definitely, it will be dependent on the way you're, so that is actually how you're implementing one. But then you could also use the Java semaphore, because you have that. And that actually comes with two constructors. But let's discuss about one. So yeah, so you have two constructors just providing and accepting the amount of resources as you have in here within it. And then you have another constructor on which you have an additional parameter, which when you're providing false is like providing false to the reentrant lock. Therefore, you're not guaranteeing the FIFO-ness because that is not important for the logic of the program. Otherwise, you could provide a true argument, therefore ensuring the fairness of the overall implementation. And then in here is actually the same implementation, but without using custom Java monitor, but actually using horse monitor. So in here, I'm explicitly using the reentrant lock, and I'm explicitly creating a new waiting condition. And their value is the thing that I'm using for determining the amount of resources that are available, while waiting here, differently from the previous exercises that you've seen, on which I'm just signaling no matter how you have actually processes waiting for something or not, is also used to get whether you have processes waiting. So in here in this implementation, I'm also adding an additional variable waiting, counting that. And the rationale is the thing that we were seeing before. So if you are just doing this before and after the wait, then you know that before waiting, you are incrementing the waiting value, and then decrementing that straightforwardly after the wait guarantees that we have a decreased number of processes waiting, and then given that in the monitor only one process at a time will have access, then you're having this kind of situation. And then in here, then the other thing that you're doing in the release, differently from the previous implementation or the previous algorithms that we were seeing, we're also checking how many threads are possibly waiting. So that is done because in here you don't have a strict requirement on definitely doing acquire and then release, but some processes could invoke a release nevertheless. So it's not that just having the value will guarantee that there are new processes running or something like that. So in here you're also explicitly checking whether you have at least one process waiting, and only on that occasion definitely you're sending a signal, otherwise you are not sending a wasteful information that might cause like extra delays which are unnecessary. And in here I'm also providing like the intuition of which are the differences between signal and release. So the thing is that if you're seeing the signal in here, so the previous implementation for the conditions, then you have no effects on the. So the fact that is referring here is actually not no effect in terms that the other thread is actually not waking up, but in terms of signal being remembered. So the main difference is that in there, you could also send a signal to signal that the condition has finished, but if you have no other process waiting for the condition to happen, then you're losing the signal. In here, on the other hand, you're keeping that information. So it might be seen like something straightforward to do, and so for example, well, if I have bad code, and then I'm using semaphores, then that it will adjust for me. Still you have logic problems in your code, and the problem might be somewhere else. So also Semaphores makes condition for waiting condition more finicky and more difficult also to check properly, because they're not very well bounded, and you could also invoke an acquire or release elsewhere in the code and need to check all the possible circumstances. But in here they are more contained with with monitors. Then you have await versus acquire. So you have that the other condition is that while the await is always blocking, because definitely given that you're not counting the number of resources, you're just saying, I want to wait for a condition. So that is the await that you have. In the acquire, you're not blocking if the number of resources is actually greater than 0. And as a consequence, then you're only waiting if you have no resources being available. So you're waiting for a condition that will be triggered by the invocation of the release method. I don't know whether we have another explanatory slide. Yeah, but before we add details, questions regarding this preliminary definition? Then, you see, definitely the other thing that you could also do is to also have acquire and release on different paths. So you're not bounded by having a lock and unlock for guiding the critical section, because you're just waiting for a condition to occur. So then, therefore, T1 could only wait if the event hasn't occurred yet, and then that is actually going to signal, okay, now the event has occurred. And so by invoking the release, if T2 runs before T1, then T1 will immediately know that the condition occurred, and that potentially also changes the Boolean variable that you see. Then you need also to ensure that the invocation of the release actually entails a modification of a Boolean condition which is tested by T1. So it adds also some kind of logical overhead, which is still included in the monitors in a more clean setup. Because in here you're not providing necessarily a critical section, you're just waiting for a condition to happen. But you could also use Semaphores as mutexes, as locks. That's for sure. And in fact, given that you're not bounding a recent condition, then in the third point actually points out that there could be also a recent condition. If T2 signals the event, and then T1 just waits to wants to decide to wait for the event. So that is actually something that might happen, but definitely okay, let me revise that. So you might have a race condition in terms that you're not guarding a critical section if you're doing that. And so maybe you're testing the variable and or you're doing something else with the code, not necessarily testing the variable itself. Anyhow, this kind of Semaphores, as I was mentioning before, will prevent for the lost wake up, in as much as if you're trying to acquire and the other one is trying to release, then you'll be non-blocked. So T1 could continue with their computation. So they were just targeted of solving this theoretical problem, and then they also went implemented. So the other thing is that, as you might see, you could also have like a binary semaphore, which is not just a semaphore as you might find online in some other material, initialized with 1 as a parameter, but actually a semaphore implemented in a different way, on which you have the maximum value that you could achieve, which is 1, and the minimum value that you might have, which is 0. So anyhow, you're always waiting for a condition to happen. And therefore, as a consequence, you could actually use a binary semaphore that could also be used as a lock. So this is going to be different from some of the material that you find online. So that's why I'm saying, yeah, you could also use online material, but some of that might be wrong, because it's not theoretically correct on the literature. So, yeah, initialized to 0, because that actually tells definitely that you have no resources. So if anyone is trying to invoke an operation, is trying to stop that as much as possible. And that is just like a verbose specification. But let me show actually in a more concrete idea of what is the binary semaphore that I'm blabbering about, and then we're going to go back to the explanation. The binary semaphore, as I was saying, is actually going to check whether the arguments are either 0 or 1. Usually, as per prior definition, they are initialized to 0. And then you have basically two semaphores, one which is initialized to whatever the value that you're providing, and the other one which is going to be initialized with the opposite. So the aim here is that you are invoking, in order to acquire, for example, the resource, you're going to run the acquire method first, and the second one is trying to release, and then the other thing is actually going to do the vice versa. So one is going to acquire something and then to release, but in the opposite order of the semaphores. And that is done mainly to avoid race conditions. So what is actually the idea? The idea is if you have one process acquiring, then and you provide it as an argument 0, then you try to acquire the S0, and then that will actually stop. So you're waiting on the S0 acquire. And in order to continue, you need to wait for another process to actually invoke the release method. So with the release method, you see that you're invoking S1 acquire, so that increments the semaphore that was initially 1. Yes. So that actually decrements the initial semaphore that was S1 to 0, and then it will actually invoke the release on S0. As a consequence, by invoking the S0 release, then that will release the other process waiting on S0.acquire. And then that's why you are actually ensuring that the computation goes on. And then after that, S1 is going to be incremented once more. So the other process you see, once you have someone that acquired, then, and if you are releasing S1, only after the release of S1, then the other process will be allowed to release. And just to show the behavior of this kind of weird binary semaphore, you can also see that what if a process tries to release that twice, then you have an S1, so let's go back to the initial state where init is 0, you're trying to acquire, therefore you're incrementing the semaphore S1 to 0, and then you are releasing S0. So if 0, semaphore is going to be incremented to 1. But you see that is actually abiding by the specification that I was discussing before, because then afterwards you are acquiring again S1, but given that you are acquiring that again, then you'd be blocked because S1 now has a value of 0, and by the definition of a semaphore, you're going to wait. So you are forced at this time to someone to call and acquire in order to continue with the computation. So you see that that is one way basically to guarantee also mutual exclusion and to guarantee like an access to a critical section, and that is actually what they're used for. Yeah. So in here, that is also what's called binary, because given that you have either a state of 0 or 1, it's just reflecting whether one single resource is available at the time. And either there is someone acquiring the resource, and therefore very likely have very single resource on hold, or is actually available, so you could take it, or you cannot release more than once, and that is actually not allowed. So you need someone that actually is going to acquire that back again, so the variable could be decremented. And therefore, in this scenario, whenever you are assuming that the resource is initially available, then you're initializing the binary semaphore to 1. Otherwise, if you want to say whether an event has occurred, and then you have only one process checking for the occurrence of the event, then you're initializing that to 0, under the assumption that you start with no event being occurred. And the slide that you've seen afterwards is actually the solution of exercise. Yes?
Could you please go back to the previous slide? I want to show you something.
So just the definition of a binary semaphore? So this one or the actual previous?
No, this one.
Okay.
In the constructor right now,
Sure.
for the S0 and S1,
Uh-huh.
why don't you just, why are you creating new semaphore? Like, why aren't you kind of like just assigning it to the init kind of like variable? Instead of saying like S0 equals init and S1 equals 1 minus init, why are you creating new semaphores?
Because I'm using that for arbitrating the access to the resource. So this is actually the usual theoretical mindset whenever you're trying to show that something could be implemented by using something else. So here I'm actually showing that the binary semaphore could be implemented by using the actual semaphore that you had at the very beginning. If you want, you could also basically implement a binary semaphore using a monitor and checking for just the variable in it and checking whether that is 0 or 1 and checking how many processes are waiting or something. So if you want, you could also implement everything from scratch, and that is actually fine. In here, you are actually achieving the same kind of behavior in lesser amount of code. So in here, you're basically using a semaphore because now S0 and S1, they are not just counters, but are also providing you the waiting ability on the specific number. So if you're just using S0 and S1 as values, then you need also to use, in addition to that, waiting conditions. And then you can do that, for example, by using a monitor or locks or what have you, but then you need to explicitly add the waiting conditions. In here, you're using the semaphores automatically in an interleaved way to achieve the same desired effect. So the answer is, in code, there are multiple possible correct answers, and this is not the only possible implementation. So the second part of the answer is, yeah, you can also use S0 and S1 as single integer variables, but then after all, then the only thing that matters is having an init, because if you have S0 and S1, one is just the opposite of the other. So you could just boil down everything to init, and that's fine. And then you could also take init, but then you don't have just waiting conditions, and then you need to implement those. So the idea is you could also implement everything from scratch, but then you need also to structure how you are waiting precisely. I don't know, does that answer the question? You have follow-up questions, anyhow. Before
entering the, let's talk about let's dissect it a bit. Before getting into the constructor,
okay.
Right now there are two variables semaphores. They're pointing to two different memory locations. Am I correct?
Yeah.
Once you enter the the constructor, you're not using those memory locations anymore. You're just creating another semaphores each time.
But that is actually a problem on how you're using the class. So they should be used similarly as you're using locks. So there should be a binary semaphore which is a shared resource, like the chip distributed signaling device. So that goes down to the same argument of recreating all the time different locks. So even in here, if you're creating different binary semaphores all the time, then just only one process is going to have access to that specific binary semaphore. But that goes without saying that you need to initialize a binary semaphore to be shared across sprites. And then if that is a global variable, then that could be used. So you could see that as a monitor, and that goes without saying that even the monitor, you're not creating multiple instances of a monitor across the board. if you're thinking about like design patterns, it's like your resource is going to be like a singleton. That is actually the rationale. So whatever is shared needs to be actually shared, so you need to ensure that you have a unique instance. So in the coursework, we're not using like the singleton constructor, just creating one single object, and that object is going to be accessed globally through the threads, for example, but that is actually the same idea in here. Definitely, if I'm creating multiple instances of a binary semaphore, then S0 and S1 are never going to be shared. But if you're having one object, then the variable S0 and S1 is going to be always the same across the board, because the object binary semaphore is going to be the same. Does that answer the question? So that goes without saying also for the same argument for integers. Even if you're using integers, then those are not going to be shared anyhow. So even those should be like static variables. But most importantly, given that you are bounding within a critical section, the most important thing is that the monitor that you're using needs to be shared, not actually the variables itself. Because the variables needs to be protected by object encapsulation. So the thing that you need to share is actually the binary semaphore, not the variables themselves. Okay, good question, by the way. Any other questions while we're at it? So in here I'm just skipping that on a fly just because definitely you're seeing the same ideas all over. So in here I'm just repeating whatever was already conveyed implicitly, but let's just revise that for the sake of clarity. So I'm trying, so those then could also be used to use mutual exclusion. So given that you have an occurrence of a one single event, or definitely you are waiting for a resource to be free, if you're using like a binary semaphores, then you could also use that to implement a lock. So that also goes with the argument to the discussion of one other of you that was asking me on Friday, could also use binary semaphores to implement monitors, or in other way, what is actually the difference between binary semaphores and monitors or locks. So this is actually the other part of the answer, which is how could I implement a lock, not a monitor, that is actually discussed more deeply in the research paper that is provided, but still, given that you have an access to one single resource, then you can also achieve mutual exclusion. Because even in there, you're going to have like the same semantics, so given that you have a value which could be either 0 or 1, even though, so you're also preventing bad usage implicitly of the, of the locks themselves, so they might provide additional safety guarantee to the cost of having a deadlock, so that is actually the only problem. So the idea is that you could also use acquire and release interchangeably as lock and unlock. That is what I meant. So you could also use acquire and release as lock and unlock. But with lock and unlock, if you're unlocking something, then you could also unlock multiple times. To no avail, and is going to act as you're unlocking one time if no other process is basically locking the resource. But in here, you cannot do unlock multiple times. So the difference also is that while on locks, the unlock is non-blocking, this release is also going to be blocking, and therefore also the, also the unlock associated with that is going to be blocking. So you might see a deadlock whenever you're using the protocol for locks in a bad way. That is also something that was not written in the slides. But anyhow, while I was running the code visually, I was showing you, so in this slide, how that works actually as a lock, and how if you're invoking 2 times, the release actually is going to be blocking. So you need someone invoking the acquirer. So then you have to ensure the additional correctness guarantee that you're using the binary semaphore actually by abiding to the protocol. So if you're not abiding to the lock protocol, then it's not going to behave properly. Because we're guaranteeing mutual exclusion, but then you have additional waiting conditions that are more problematic to handle. Yeah, so, and that is actually the thing that it also goes without saying. So given that the semaphore might be initialized to 1, if you have like a contention on which should access the resource, at most 1 will succeed, but that is actually by definition of a semaphore initialized to 1, because 1 will decrement that to 0, the other process will decrement that, attempt to decrement that will have potentially negative value, so it needs to wait that value becomes 1 again after the release of the resource. So actually we need to wait to become 0 and then eventually to become 1. Yeah. And that is actually the short end of that. And this is actually the slide that I was trying to fly into. So given that you have a lock and unlock, definitely you could initialize a binary semaphore to 1, just to show that you could directly lock because the resource is now available, and then you could invoke the unlock method down below. So definitely the thing that you could do is implementing a different kind of lock being a semaphore lock. So even here, then you could also ask, why are you implementing a lock using semaphores? Yeah, too long did I read, and question answer is actually why. If you can't do that, then I'm showing you a way. The second way is that if I'm showing you different possible ways to implement something, that is the only way I could reply to the question, how is this different from this other one, or which are the similarities? So this is actually making explicit of which are the similarities between binary semaphores and semaphore locks, with additional caveats that I provided regarding the unlock itself. And definitely then, but it's just the other way around. So I could also say whether an event happened or not by just, as per prior slides, changing the initialization value to 0, and therefore as a consequence, then you know that you have something awaiting for an event to happen and signaling that just one event happened once. And there you have similar semantics. And that is just recapping everything that was discussed before and in words. So in here is actually showing, as I was discussing before, and that also boils down to the same slide that we've seen at the very beginning. So this semaphores for signaling, and it's actually just restating the same idea all over again. So that is restating first the thing that I was replying to your colleague. Definitely the binary semaphore needs to be shared, as also the monitor needs to be shared. Otherwise, you don't have like a distributed access resource to be shared across threads, and everyone is just asynchronizing within itself to no avail. And in here, actually, you can also show that if I have basically two processes on which someone is trying to say, okay, the resource, so the event happened, and the other one, which is waiting for the event to happen, then that could be like detached in two parts, one just waiting for an event and one just signaling for the occurrence of an event, which, by the way, you cannot do with the locks, because that protocol is just for guarding a critical section, but they're actually not counting basically the amount of resources being there. So just it will just create like bad race conditions because you are trying to safeguard in a different way, but actually it's not going to act. So using locks in the same way instead of proprietary and verbogen is not going to work at all. And there just show restating again that you could also implement a semaphore using like the synchronized keyword, and that was provided at the very beginning just to give different flavors of the same implementation. Any question? That is restating once again the problem of a lost wake up that you have on monitors if you don't have a process which is basically waiting for a condition. So that is just in a very verbose way the thing that I was just discussing also on Friday, but just to recap, also restated also at the beginning of this lesson, which is the semaphores are trying to avoid the problem of a lost wake up that might happen whether you are not abiding by the protocol in a strict way, and you're doing that basically by remembering how many resources were released. So by using conditions, if you are signaling that a condition happened but you have no other process to check the value, then someone might wait for a condition indefinitely and the wake up signal is lost because you were sending the signal before actually the process started to wait, and so the other process will not wake up. But that, as I was saying, is just for me bad design choices. So if you're designing the choices in a good way, and given that everything is guarded by a critical section, then you could remember the lost signal by setting like a Boolean value in a variable or changing like a resulting Boolean condition, for which then you're creating like a conditional dependency whether you need to wait or not for a resource, because if there's actually no sense for waiting, then you're not invoking the wait at all. So that is actually the way to fix this kind of lost wake-up problems in monitors. You're just adding one extra memory for a variable. But if you're too lazy, then you will also use semaphores somehow. And they will remember the event happening for you because they have an internal counter. And that is the way you're remembering basically the signal that you're sending. And in there is actually whatever is written is actually that in a more verbose way. So in here you could acquire to a point where condition is not possible for this operation and acquire operation on the same semaphore to execute simultaneously, because you're implementing those through synchronized keyword as I was showing before. So you need to also assume that all the acquire and release work like within a critical section somehow. So in here, if you're releasing before the acquire, therefore you're incrementing the counter, and if you're trying to acquire before the release, then you are waiting for the condition to happen. But if you're invoking the acquire after a release has been invoked, then you're just implementing the counter and then you're continuing on. And basically the way on which you could avoid this kind of waste signal is, as I was mentioning before, in here, incrementing like a value, and then using that value as a Boolean condition. So that is actually the concrete use case example. So in here, I'm just waiting if the value is equal to 0. In this way, you are avoiding the signal to be lost. So there's always a way, if you have a bad implementation, to avoid issues. So you are not necessarily forced to use the semaphores. It was just like a theoretical contraction to do something concisely and in a minimal amount of code, basically. So in here, then I have some kind of conclusions just to wrap everything, and then I'm just going to discuss one of the examples, because the other one, which is how to implement basically a scheduler through the usage of semaphore, is going to be beyond the thing that I'm asking at the exam. I'm not asking you to remember that kind of use case example, and it doesn't actually solves any kind of doubt, or is just narrowly like a theoretical contraction to show that basically I could define a process which is actually the scheduler, and the scheduler needs to wait for the clock tick And so that is going to be the resource that I'm waiting for, and then each thread will have a separate semaphore on which they're waiting to acquire in order to continue their computation, and eventually they are releasing their computation to the scheduler, which is then saying, okay, now you need to stop, and then they are arbitrating which is going to be the next thread to be run. So basically it's showing that you could also have like a use case application of this waiting condition in a distributed way without necessarily using locks. But the code is there, by the way, and the explanations on the slides, but it's not going to help understanding critical sections too much. It's just adding an additional layer of complexity to what I'm concerned. So for the conclusions, then you have that semaphores. Basically, the pros is that they're limiting the busy waiting sections to just the acquire and release operations. What does that mean? So it also is similar in the same way that you're achieving that with read and write monitors. So the thing that you're doing with read and write monitors, as we discussed on Friday, is how do we ensure, for example, that multiple threads will access the same critical section, because we gathered theoretically that all the threads are doing a read operation, and so all the operations could be read concurrently, write concurrently. Then the thing that you're doing is basically restricting the critical section up to the entire region, otherwise you need to ensure mutual exclusion to no avail, and therefore you're creating minor critical sections just at the beginning of the critical section, so at its boundaries begin at the very beginning and at the end. And here, similarly, given the implementation of the binary semaphore, I'm just showing that I'm postponing or also providing, that is actually how it works under the hood really, that the access to the mutual exclusion is actually mediated by actual areas which are mutual excluded at the very beginning and at the very end of the critical section, on which I'm providing like semaphore implementations. On which I'm actually using safeguarded operations which are using concurrency control. And they could also avoid the problem of a missed signal by representing the availability of multiple resources at a time. And semaphores require that a user shall always call the P before the V, so to follow the right protocol, or if you just want to signal something, you could distribute the P and the V. But still, you might violate as much as you wish the protocol, but then something weird might happen. So those are also meant to be used, that you need always to invoke the P before the P. And I provided a use case example that if you're using semaphores for implementing locks, by using binary semaphores, then while on locks you could unlock multiple times to no avail. In here, if you're using binary semaphore, then the lock operation is going to be blocking. So that is also witnessing the kind of problems that you might encounter by using semaphores in the wrong way. So they are more delicate to treat. Semaphores do not necessarily remove busy waiting, because if implementation, so that is also to evaluate from some of the slides. So some of those are just saying that semaphores are removing busy waiting. But the thing is, it depends on how the underneath constructors are implemented. So if you're using like a waiting condition for the monitor, which is not using the scheduler, but actually is using a busy waiting, then you're not removing the busy waiting by itself. It's just dependent by the way the actual semaphore is implemented, and that will constitute whether you're removing busy waiting or not. So, and we're going to see after the break actually an example on how to achieve mutual exclusion through busy waiting, so to provide like an idea on how you could achieve that without any kind of sophisticated controls. Semaphores represent a low level mechanism of synchronization, in as much as you don't have like a mutual exclusion and then a condition to wait, and then you could do that, but it's actually more difficult to achieve. So there's actually a logical contraption in which you are writing a monitor, and then you have like a rewriting mechanism that is going to tell you how to put the semaphores, but it's going to be more complicated than anything else. And then just before the break, I'm just providing this example of producers and consumers. So the idea here is that we want to implement like this kind of bounded buffer by one single element, but just by using semaphores entirely and without using any kind of locks. So that is also possible, and also showing that you could achieve the same stuff in multiple possible ways. So it's not that once you achieve one, so in computer science it's not like in math that you have an equation and the outcome should be exactly the same number, otherwise you did your operations wrong. The notion of computer science is that the program is actually not the final result that you're doing like in a mathematical formula, rather than the different way you're obtaining the result, okay? So it's similar to say different people might achieve different passages or different operations in order to achieve the final result, which is the outcome of a computation. So that is actually the procedure. A program is just the procedure of doing something. And so there might be different procedures actually achieving the same goal, which is actually the final result of a mathematical equation. So that is because whenever you're writing a program, is actually like writing a theorem, so to speak. So you have like something comes from the theoretical literature, which is so there is an isomorphism between programs and proofs, and that is basically what you're doing. And definitely you could write different proof styles for proving the same kind of outcome. So, and that is actually the idea. A producer thread repeatedly generates new messages, and then you have a producer that is going to consume the message that is going to be, and the consumer is going to consume just one object produced by the producer itself. So you need to synchronize those two somehow. So, and here, then how are we achieving that? We're achieving that in the following way, on which you have a message which is initially null, just signifying that you have nothing to be shared. And then you're using basically the producer to a binary semaphore of 0. What is actually the rational? The rational is that you mentioned that no event associated with the production of something occurred. And so basically you are initializing the produced to 0. And the consumed is going to be initialized by 1. So that is actually more counterintuitive. The idea is going to be that if I'm trying to so I need to reset the consumed to 0, so to guarantee that it actually will be consumed. So the idea is that the consumed, if I'm trying to, actually it's going to be better if I'm showing you the actual implementation. Yes. So that is actually one way to implement it, using a buffer. So in here, you are basically trying to say that I cannot access So basically that is creating, as you say, mutual weight for the operation to continue. So the thing that you are ensuring is that you could also do that in a different way. So the other question is, why on earth we did it this way and another way? I'm going to show another example on how you could use basically 3 semaphores. That is one possible implementation. It's just to showcase that you will also interleave like the waiting and the release operation. But there is no peculiar reason why it was implemented in this way. It's just because in order to release the consumed in here, then you need to also put, so the other object needs to acquire beforehand. So I'm acquiring the thing that something has been consumed and therefore I'm decrementing that counter to 0. And then I'm setting back the message, and then I'm waiting basically someone to read the value. So that is actually what this code means. On the other hand, you see, if I'm trying to check whether something was produced, in here I'm waiting indefinitely on the get unless someone says me that the message was produced. And in here, weirdly enough, these two waiting conditions are switched, otherwise it would have a race condition. So the thing that you have in this implementation is that first you are acquiring the consumed just to say, okay, now I'm starting to actually providing the value. So whoever was getting the message before was already consumed. So the rationale is, even if there is no value, you are feeling assuming that the previous value, which is none, was consumed. So it's actually quite convoluted, but it's like in logic, is like true for vacuity. So given that there was no message, then that was backwardsly acquired, consumed. So that's why you have the consumed initialized to 1. That is the logical reasoning associated with that. Then, given that you're consuming something, so you're saying, okay, it was consumed, so I could continue, because the resource initially was consumed. I could set the value, but you see, at this stage, still the object is waiting, the get is waiting on the acquirer, and that is actually requiring the put method to invoke the release, and only when that will invoke the release, then I'm allowed to read from the local buffer. So by interleaving the way I'm waiting for the concurrent and for the actual value to be get and retrieved, then I'm actually achieving mutual exclusion. And similarly, while I'm getting the value, I'm waiting to be consumed, so another thread trying to do a put will not be allowed to put a new value unless I'm sure the previous object reference is safeguarded in a local variable. So only after the consumer will actually consume after setting the previous object to a local buffer, then the put method will be allowed to put a new value inside. And then you have basically the wordy description in here, which is the same description that we have across all the slides. So the put is just wait that the buffer is actually empty, and the get needs to wait that the buffer is full, so you have at least one element. And then you're achieving that in this way with semaphores. Any kind of questions before I further complicate this example with 3 semaphores, and then we'll have a break? Yes?
In the Peterson consumer, how that Peterson know the consumer not need more message?
How does the consumer knows that there is no message? You know that through semaphores. So you're trying to check whether a resource was produced at all. So given that you have a binary semaphore, the get will try to invoke acquire over the produced initially, and the produced will be initialized to 0. At this stage, you know that there are no resources available, and so you're waiting. Okay?
I mean, how that producer know the consumer don't need more message?
How the consumer knows. So initially, you're assuming that the message was already consumed because you have a null value. So that value is like, yeah, now I could write a new object in the buffer because the buffer is empty. So for me, the initial condition is either someone consumed the object or the buffer is empty, which is the same. So the only thing that the producer sees and checks is whether the buffer is empty. Because if the buffer is empty, it's like if someone has read the value. So the put will always be allowed to put the value if the buffer is empty, because consumed will be acquired. So you see initially it is at 1. But then let's suppose that I'm trying to put the message twice. Okay? So I'm allowed to say consumed because the binary is initialized to 1. I'm setting the buffer and then setting the producer to read. So if you have any other consumer, will be allowed to read the value. But let's suppose that I'm very fast and I'm trying to put another value. At this stage, the consumed.acquire will be blocking, because now you have a binary semaphore that was previously 0. Now, in the previous call, we decremented the counter to 0, and now the value is 0, and you're trying to acquire the binary semaphore. At this stage, then the binary semaphore will be 0, and so you'll be waiting. Okay? So you know, by you previously decrementing the counter, that you already read the message, basically. And so you know that you need to wait. So the semaphore knows that by keeping in its memory a counter, that you already did the operation before. So you're not actually checking whether the message is null or not. You're just checking with a counter, and the counter are acting on the behalf of the buffer. Okay? Okay. Any other question or any kind of follow-up question? Then I'm just going to briefly show how we could create also a bounded buffer by using a different kind of mechanism. By having like a mutex, an empty buffer, and a full buffer. So in here, the thing will be actually more complicated because I have a queue of messages, and then I want to have different kind of semaphores. In here, before I had 0 and 1, just to mean the number of available resources and the amount of reads. In here, you could just generalize to have, instead of having a 1, you're having an n, so the number of available resources, or the other way around, the number of empty slots. So in here, the resources that are available for the empty are going to be the number of slots that could be written, and the number of resources that are available for the full are actually the number of elements that are within the queue. So that's why, basically, you have the same implementation as before, but you have like the size, and so you're generalizing 1 with n, basically. But due to overcomplicated stuff happening in semaphores, then given that you are going beyond binary semaphores, then you also, if you're having a good look at these, those are actually looking at a buffer acting as a binary semaphore implemented through binary semaphores, so to speak. So that is actually what you're achieving. In here, we're trying to generalize the former example by having one of the 2 semaphores now initialized to n, which is the number of overall available slots. And just to provide like the rough understanding of how it works, then you need to have a mutex actually guarding the queue. So that is only used to guard the message queue, because now you don't have one single variable, and therefore you need also to ensure something else, that you have like a concurrent access to a data structure, so you need to protect that, so the mutex is not actually guarding the method, but just the access to the message queue. Because, how do you say, I'm not using on purpose like a linked blocking queue, otherwise you can remove the mutex entirely and use actually a linked blocking queue. That could also be like an additional way to implement the same kind of stuff, but in here I just decided to use semaphores elsewhere without any kind of intermediate way of doing stuff. So mutex is just safeguarding the access to the message queue, and then you have empty and full actually working in a similar way. So you're checking empty.acquire to say, okay, now I have one element that could be written, and therefore, okay, I could acquire 1 free slot to write. So that is actually the thing that it's trying to say. And as you can see, then multiple processes could acquire the empty, so because you have 3 slots. but all those will be arbitrated by a mutex or like a lock to actually access the critical section on which I'm concurrently updating the resource. So even though I'm allowing multiple threads to change the message queue, I'm just making those access one at a time to avoid concurrency issues. And then I'm releasing the fact that now we have as many slots as the number of threads that actually put a message in here. That will also trigger the possibility of acquiring multiple resources as you're having here if you have at least one resource being available. So through acquire, you can only invoke this method only if someone added one value within the queue, because that will increment the counter of the full semaphore. Even in here, I want to remove, so I'm updating a data structure concurrently, so I need to safeguard the access to the queue. After popping the element from the queue, I'm actually releasing the queue and showing that now I have one extra slot which is now available, and then I'm returning the value. So basically you could take the same exercise and simply extend in this way to have the same kind of reasoning. So with a binary semaphore, you're just bounded to have one value at a time. In here, by using semaphores, not binary semaphores, you can also have a generalization to allow the buffer with multiple elements. And then I think that after this, you just have like the task scheduler, which is like the clock example on which you are using semaphores, but just to simulate the ticking event that is going to be obtained. And but if you have any questions regarding the task scheduler, that is not going to be part of the exam anyhow. And if you still have questions, you could also be free to read the slides and ask me about that. Besides that, any other question? So I'm giving you 10 minutes break, and then we're going to discuss the Dekker, Dijkstra, and Peterson algorithms. Yeah, hello.
I want to know why in this scenario still the result is still 200 by 2, because it only use volatile keyword. I think
no, it's just because on the specific scheduling order. It's not because you're running once and the problem does not appear. That actually, may I? So
I think there's risk condition in the thread between the threads. There are no synchronized code or some mutual expression.
So the thing is that should not be necessarily how to say. Okay, that's the question. We have two threads, and you have that. So usually the thing that might so you have risk conditions, so you have that. You're trying to think of the variables as such. So AI is not necessarily atomic for the integer survey.
Yes.
And then downloads require financial blah, blah, blah. So it might happen. So there are actually two possible explanations. One, which is actually related to the code reordering. Yes, please take the mobile phone. Thank you. So one might be also related to the code reordering. Therefore, if you have a multi-threaded computer and both threads are working on the same CPU, they're actually accessing also the same cache and the same memory. So independently from actually using the volatile, they're actually sharing the same CPU and they have actually the same access to the same variables somehow. So this is actually one possible explanation. The other second explanation is actually that you're running that kind once, but you haven't run that like 1 billion times. And eventually you would have one computation on which the issue might arise. So there are actually two explanations, just depending on your architecture, one, and the second one could be how many times you try to run the code. Because just in one run it might not happen, so it's not a systematic error that happens all the time. It's just that might happen sometime, but not always. I don't know whether that answers the question.
So I still don't know why the answer is 200 by 2.
Yeah, so I provided the answer, but I don't know whether that answers your question. The thing that I said is that there are two possible explanations. One is the architecture. So they're actually using the same variables because they're running on the same CPU. Because if you have a multi-threaded computer, they could be run in there. The second part would be related to the ways the processes are scheduled. So they might be scheduled in a way where you have still that outcome without having a race condition. Because that was not the schedule leading to a race condition, but if you're checking that on 1 billion times, it might happen. If that doesn't happen, and nevertheless, then the issue is actually that. Why I'm saying that? Because still, independently from having a volatile, the plus operation is not atomic. So that is actually the issue. So that is not an atomic operation.
Yeah.
And volatile is requiring atomicity, but just for one-shot operation. So if you're just writing a value, or if you're just reading the value, but not for increments, which are free operations. So either reason is either your machine is making the two threads working on the same CPU, for which then the problem does not arise if you have a multi-threaded architecture, or the other thing could be that schedule was not the one actually leading to a race condition. But if you're running overtimes, you might have a race condition.
Yeah, I got it.
Okay, no worries. Yeah, question.
In producer and consumer, if the consumer thread is ended, what will producer do?
If the producer and consumer, if what is ended?
If a consumer thread is ended.
Yes. So if a consumer is finished, then the producer will start producing something, but there is actually no one reading. Therefore, as a consequence, I could fill up the buffer and stop actually providing data. Then that is just a simplistic assumption on which I'm assuming like messages in a distributed computation, okay, on which I'm assuming that my messages needs to be digested. So within the code that I'm providing, I'm assuming that I want anyone to read the latest the messages in an exact order, so I don't have any kind of timeliness requirements. So in this implementation, I'm just filling in a queue and ensuring that the messages are read always in the right order. So if there is no one to read, I'm stopping producing even, because you have a restriction on the size of the buffer, be it 1 or n, and after filling up n elements, I will stop basically. So basically, I'm blocking myself. But that will very depend on your use case application, okay? So if your application requires to continue producing, like for example you're recording a microphone and then you want to get the latest data, then you could also say, okay, then I'm removing the data that was not consumed, and I'm removing the oldest value, and I'm replacing that with a newer one. So I'm just reading myself and putting one element inside. But that will be like domain dependent. So that will be strictly dependent on your application. In here, I'm just assuming that I have a queue and just taking the values that I produced, and then under the assumption that the consumer needs to read the messages in the expected order. But if you have like real-time requirements, then you could also force that. It will be very dependent on what you want to do with those.
Oh,
Okay?
okay, thanks.
No worries at all.
Thank you.
No worries. So before I start again, any question? So the last part is going to be quite tedious, so let's try to make that as interactive as possible. Okay? To how, let's see, because actually in here you also have answers and stuff like that, so I need to double check how to make it interactive as much as possible. Yeah, I could also do like that later on. Okay. Just show one slide at a time, so you see a lot of back and forth just to hide the solution. Then, if you're cheeky enough, you can also look at your computer and find the solution. Anyhow. So what are those algorithms? Those date back to the dinosaur era of computer science, in which you have no like scheduler, or because you didn't have like multi-threaded computing, most of the programs were just sequential, and you didn't have like multi-threaded computers. So most of these exercises were just like, now you have like quantum computing, which is just merely theoretical contraction that real life use case applications. And in here, concurrency was somehow similar. So it's just like fantasy world. So, and nevertheless, research continued in order to seek for the having concurrency requirements. Well, that's why theoretical research is important and not just practical one. So Dekker provided a solution that can be provided logically correct. But we're not going to discuss directly why that solution is logical. I'm going just to provide brute force attempts that are going to be refined in time just to show why the final solution is correct. Okay? The final implementation is correct. So you see that they get back to 1965 once you have maybe UNIVAC or this kind of old dinosaurs running around. And therefore, there was a simpler solution, but that was conceived very later on. But we're going to see how the history will develop in a short amount of time. So in here they are also using the assumption that you have some kind of interlock property, and you have atomic reads and write operations on singular memory locations, so that is actually the only assumption. So you're not even using test and sets or nothing at all, just atomic operations on one single variables. So they can also be implemented in straight and plain Java. And so in here, so the actual paper provided a new general implementation for an arbitrary number of threads or processes, but in here, just to be simple enough, we're going just to assume that you have two processes, 0 and 1, and those are going to be the names associated with that. So the thing is that also Java underneath, whenever you're scheduling some kind of things, is also checking which is actually the thread which is doing something, and that's why you have names associated with threads. And so let's go to discuss these solutions, but let's go with actual. Let's see if I'm able to. Let's do it this way. So this is actually the first attempt. The first attempt is the following to achieving the algorithm. So we want to implement like a critical section, so with a lock and a lock. And let's see what is actually the problem that you might have in here. Okay. So I'm just describing the code, and let's see if you have like the solution for that. So I'm having like my lock, and I'm remembering which term it is. And I have like a other, which is just showing, which is the opposite value. So in here I'm just doing like mathematical contraction, but that is just returning 0 if I provide 1, or vice versa. That is actually achieved by using the modulus operation and incrementing by 1. So if you have 0 plus 1 yields to 1, which modulus is actually 1. If I'm using 1 plus 1 yields to 2, the remainder of the operation is actually 0, and therefore the modulo operation returns 0. So in here, I'm just checking whether the current turn is actually different from mine, and in this scenario, I could continue. So you see in here, I work under the assumption that the lock is actually turn, which is, so if it's different from I, then I need to wait. Otherwise, I could continue my computation. And you can see that if I have 0, then the value is going to be 0, and so 0 different than 0 is false. Then I could continue the computation, and then after I'm using the protocol under assumption that I'm using the protocol correctly, then I could unlock, and then I'm setting up the term to be the over process. Now, if you have the other thread trying to do lock, you could be checking that 1 is actually different than 1, and then you could continue. What is the blatant reason why this code is wrong? And what is the issue arising from this? So one thing is actually to achieve critical thinking. So I was just forcing you to see the code was correct, but it's not correct. I'm just showing you the computation where it is correct, okay? So what if another thread starts, and what would happen? So what if thread 1 starts and is checking for the while condition? What would happen on the lock? So if the thread 1 is starting and if its I is equal to 1, then you're going to use while turn is different to 0, while true, and then you're continuing to loop all over again. So you see in here, the thing that you're having is you have an unnecessary delay of actually have a starvation. So you have a starvation under assumption that the other thread is actually going to acquire eventually the critical section. But if you're having just one thread, which is not the example from the assumption from the exercise on which you have the assumption that you have still two threads and still someone actually checking for the condition, then you have like a starvation, because then you are unnecessarily waiting for a condition to happen. Therefore, this other thread was the only one. There was no other thread trying to acquire the critical section, and therefore, as a consequence, then you're having an unnecessary wait. So the solution would be something guaranteeing that no matter the value provided in there, I would be able to acquire the exclusive lock, even though without waiting for the right order of threads of being scheduled. Questions regarding why this has a problem? Because by having no answers, I might assume that everyone of you thought that it was actually the right solution. But do you know, is that clear why this is wrong then, after the explanation? Just waiting for a few seconds. Okay, then let's go with the second best attempt. So it's like saying, so given that for one that did Shakespeare is like seeing the bad quarters before actually seeing the good quarters, but anyway. So this is actually going to be the second attempt. Okay, so in here I'm creating like a class which is actually a flag, which is trying to amend from the previous issue. And this has just a Boolean value, which is initialized to false. Then the thing that you're going to do here is actually checking whether the other thread is actually accessing the critical section. And definitely the thing that you're doing is, I think that in here, yeah. Okay, so you're just checking whether the other thread is willing to access the critical section, and while the other thread is actually is already there, so the other one which is different from myself, then I'm waiting, and I'm doing a busy wait for the yield. Otherwise, whenever that other is set to false, and that is done by this finished in CS, which is actually the unlock. So after the other one goes out of the critical section, it would say it's willing to access the critical section to false, and then the other thread will be allowed to continue. But what is the blatant issue that you have in here? So are we achieving anyhow mutual exclusion at all? And what is actually the problem with this code? So it works if I'm using like one thread at a time. But what if multiple threads are trying to check the while condition contemporarily? So you see, yes?
Is the problem that you keep creating new flags?
No, because that is just providing within the constructor on top. Okay? So that is not even the issue. The issue is within the testing itself. So let me focus your attention on the while part, okay? So here, if I have one thread running after the other, so in a sequential way, then you're checking for the while condition, initially it's actually false, determining that the other thread is not willing to access the critical section, and therefore, as a consequence, then I'm allowed to go inside the critical section and I'm setting my own flag to true. Then when I go out of the critical section, I'm setting my value to false. Okay? But what would happen if you have multiple threads trying to invoke the while construct? Do we achieve mutual exclusion or not? That is the question. Thanks for the answer that allowed the way to clarify the code. So, what would happen if you have multiple threads trying to check the same while true condition, so the same while condition, and if no one has entered the critical section yet? what will all the values be? No, they will always be false initially. So given that all the values will be false, then you're doing like avoiding the mutual exclusion. Two threads can enter the critical sections contemporarily. So that is the issue. So you're accustomed, given that you were working as students now, that you were spoon-fed the right solutions all the time. But that doesn't help too much if you need to check whether something is correct or not, and then you're just having ex cathedra solutions. So I'm telling you this is actually right, but it's not going to work in the real world on which you are on the wild, basically. So you need more critical thinking. And that is actually the thing that I'm trying to achieve here. So the thing that you're providing here is a wrong implementation due to the fact that all the values are initialized to false. So if you have a concurrent access to the value, given that you don't have a critical section, you don't have synchronized, then you have multiple checks of the value, and all the checks for the opponent are going to be always yielding to a value which is false. Therefore, all the threads, both threads are going to access contemporary to the critical section, and that is what the issue is about. So, you see, we're trying to create an argument constructively. Beforehand, there was an issue regarding the unnecessary weight. Now, by trying to avoid this problem, I create another issue, which is concurrent access. But we're getting there, so we have over 4 attempts before we find the final solution. Any questions regarding this as a follow-up to this explanation? Why actually the solution that I provided now, the motivation that I provided now is sound.
My question is just about the syntax. What does that other parenthesis I mean?
Which parenthesis? Sorry.
You're accessing the kind of the index in the desired CS in while loop, the other. No.
Yeah, the other is defined similarly as in the previous slide, which is just providing other. So I'm just not repeating that all the time, just out of clarity. You could assume that if you have one, that is going to return 0 or vice versa. So it's just always providing a value for the other thread. So we're never changing that method. Thanks for the question. So those are going to be the same across all the slides remaining. So the other is just the opposing value. Okay. Then you see why that will escalate up if you have multiple threads, because you don't have just an other method, you need to do something else, but it's more like a theoretical contraption, and that is not still going to be relevant for the discussion, so we're just reducing everything, boiling down everything to 2 threads. Any other follow-up question? Okay, let me do this kind of finicky stuff all over again, given that I don't have animations in my slides. Well. So now we'll try to amend that other exercise again, on which you see evident here under the assumption that all the previous code is kept intact as it stands. So I'm not providing all the variable initialization. That is going to be the same. I'm just showing the changes, so it's just to be an incremental update. Okay? So here I have always an lock and unlock. And here I'm trying to achieve this in this way. I'm setting that I am desired to check and gain access to the critical section immediately. And the other thing that I want to try to do is basically do the following. So we have a desired CS. I'm saying now I want to go inside. So just to avoid the problem that you had before. And then here the other thing that I'm doing is, as previously, checking whether the other thread also wants to access the critical section, so that allegedly should show the problem that you'd have, avoiding that you have concurrent access to the critical section. So if both threads now are immediately setting their value to true, and they're not postponing that after a while, so you're avoiding concurrent access, basically. So you are, and given that you're having that, then still you're checking whether the other threads, because you always have the assumption that the operations are run one at a time, depending from the time interval. Then the thing which you're having is basically checking that while the other one has not set the value, then you're continuing the operations, and therefore you have like busy wait. Otherwise, if the other thread it has not set itself to true, you could continue and then add the value to false. So in my description now on how to provide the algorithm, there should be more blatant the issue that you have in the code. So I try to avoid like a concurrent access by setting everything to true, but what additional issue I created as a follow-up. Yes? Yes, correct. So everyone would wait and you could create like an unnecessary wait, correct. That is actually the thing that I wanted to convey. So potential deadlock via busy waiting, and that is actually, so just so, that is more in sophisticated words, but your colleague said everyone is waiting. So everyone is waiting means deadlock. So you're having like the access. So definitely if all the values are doing true, then they're blocking everyone out. So you're just seeing the all extremes. Before everyone could get in, now you have a worst case example scenario in which both are setting something to true and they're locking everyone out without the possibility of resetting that value back again. Okay? Questions?
Does it mean that none of the threads would enter the
correct
zone at all, like any? Like
yeah, correct. So that's why it's called a deadlock. So I'm just explaining that in lay terms, as your colleague mentioned before, which is none of the threads can enter a critical section. If that is lay terms, proper methodology might be, terminology might be acquired, but it's just a matter of remembering the names. It's not like so the idea is, if you're remembering the ideas, then it's just a matter of associating the name. So it's not a matter of terminology itself. Then you will appreciate the terminology, because instead of saying them in a verbose way, both threads are, so no thread will continue the execution just saying deadlock. But that's exactly what it meant, by the way. So definitely, given that everyone is set to true, then everyone will be locked out of a critical section. So no one is going to access, and there is no other way to make it work. And that is the issue. So there's no other way. So before, in the first example, we had just a busy way. So you know that eventually you could unlock the situation. But in here, once it happens, then you're blocked forever. Any other questions or follow-up questions? Yes?
According to these programs, it's not a good way to use yield in.
So thanks for this, but it's not even related to yield. You can also have add semicolons in here. So the issue is not related to the yield itself, rather than to the values that I'm using. Yields is just to say to the processor, now I'm not doing something productive, so someone else could run on my behalf. But the issue is the way I'm setting out the condition, so the error is logical. And definitely I'm using busy waiting, so the solution is not good, but beyond the yield, it's just because I don't have like scheduler-driven methodology, and I'm just using busy waiting. So the bad thing is actually the busy waiting independently from the usage of yield. Does that answer the question? Okay. Any other question? Okay, let's see the final attempt. So the last about quarter was to say. Okay. So disclaimer, even this is not good, okay? So in here I'm trying to amend this problem and adding more construction in order to do this. So how do I try to avoid the previous issue? I'm trying to do that. Still I'm setting up the value to true, and then have one desired over value is true. Then, well, that is true. Then I'm trying to say, okay, now if you have another one which is also trying to access the resource, then I'm saying that, okay, now I'm no more interested, so I'm trying to increase the priority to the other thread so they could access the resource. So that is actually the idea. In order to avoid the deadlock, the solution is add more code in between, on which I'm saying, okay, if I have the other thread which is also waiting, then I'm setting myself to not be interested anymore to access the critical section. So I'm setting my own value to false, and that should possibly wake up the other thread, and which are going to have access to the critical section. And then eventually I will know that now myself, I wants to access eventually. But then I will be setting myself the possibility of accessing that multiple times by invoking that code on and on and on and on. And then eventually the other thread will just allow me to access by invoking once again the desired to false. And then eventually that should help the other thread to eventually check the while desired other's value to false, and that is going to go inside the critical section, so it's going to be allowed. Still, you might have other issues in here. So what if this thread, for example, is trying to run again, and then is trying to reacquire the critical section, and then it's going to check. So you might have a problem even in this scenario. And what is the problem about?
Is it that more than two threads are at the critical section and simultaneously? So this goes like contrary to the principles that you're looking for.
So you're trying to avoid that by using desired CS all the time, and I don't think that that is the answer at all. No, that is not the issue, because in there still you're guaranteeing that eventually someone will gain access to the critical section. And here, actually, the issue is more subtle. You could barely see that as an issue. You could frame that like as a starvation, but in here, it's actually framed as live lock. Live lock is just when you're live, but basically you're not doing anything at all because you are checking some condition all the time. So I need to be able to set the flag back off. If the flag is true, try again. Better, but so it's actually better for a previous solution, which would end up with both threads continuously backing off in a live lock. So you're continuously checking for the condition to happen, and you might create, for example, like in a simplistic way, you're creating some kind of starvation, multiple starvation across the threads. So one of these threads could definitely continuously check the condition, even though, and so there might be issues on one process not allowed to access the critical section. Anyhow, the solution that was provided in the 60s was actually this one, which is just a combination of the first and the last attempts. And here you see, in order to achieve something, you're adding basically most of the more lines of code, and it becomes convoluted, but then in the 80s, after 20 years, they had like a better solution. So the idea is that still you are checking whether you want to have access to the critical section, and you're using that value to say, okay, now I want to leave everyone out. I'm also checking for the value of the opponent to be the one that wants to access, but the only thing that I'm adding to the going back and forth is checking like the turn value. So I'm setting up the turn value back again. And why does that help? Because the thing that would happen is that basically the turn is going to be used to disambiguate who, in the case of contention, in the case of a life lock, is going to access the resource. So I'm going to decide who to make access. So I'm just forcing the solution to one thread. And by eventually changing the opportunity fairly to all the threads, I will give fair opportunity to each thread in different times to access the critical section. So the thing would happen is that in order to avoid the live lock while checking for a true or false, setting the values to true or false, then the thing that I'm saying is that actually I'm making the threads not to be within the live lock, so indefinitely checking for the value to be whether the value is actually true, because there could be like a very unfortunate set of events in the previous implementation on which both values were still both to true, and therefore as a consequence you always just check setting to false to true all the time, and then when all the processes were always checking for the true value, and then they were setting their values indefinitely. So that was actually what this kind of busy waiting was related about. So you were resetting the values, but they were too fast. So in order to decide who needs to go on, and just decide one process arbitrarily and deciding, but it's going to be the one which is different from the current term value. But I could also do the opposite, that would have been fine too. And then I'm deciding which process will break this kind of live lock of repeatedly setting the while true loop indefinitely, and will have access to the critical section. After that, then the other process will indefinitely continue to do this kind of check up until the other process will step desired into false, and then eventually we will give the other thread, so to myself now, the opportunity of immediately entering the critical section. So I'm not creating a starvation over the other thread, so to avoid that, the other thread will be always the one indefinitely waiting. And so we will never be backing off at the same time, and still I'm using the same contraction with the values to check whether the other process wants to access the critical section at the same time. Does that explains it? Does it? Do you have issues or questions why this is the right solution, or whether there might be problems with that too? Yes.
The condition of well if the condition of well is true, it is the thread count analog.
But that is actually solved by adding the if condition. Okay? So that will continuously be wrong, but given that you have two processes, you will avoid the live lock, as in problem 4, by having if turn different from I. So given that you have if turn different from I, you'd have that one process, once you have a live lock, will have a different value different from turn, and that will go inside the critical section. So I agree, but given that whenever that occurs, you have still two processes running that in a loop, then you're just deciding who needs to go inside arbitrarily. So I'm just deciding that the one that has their value different from turn is going to access the critical section. So I agree, but that is the reason why then they add a term different from I. So just to decide who should break this loop and continue to go to the critical section. Does that answer the question, or? Okay, no worries. Any other follow-up question? And then you see you have another solution occurring only 20 years later, but that is very common in computer science. It also happened like in graph databases. They started in the 1990s, and then they actually have a revival nowadays. But actually they started in the 2018s or something like that. The revival. So you just have waves of stuff, and then you need to wait decades for something to happen. So then the achievement is that we have like a shorter code, and usually theoretical people have some kind of a Pythonic way, but not for the way the code is actually without type safety, but merely to the lines of code related stuff. So even in here, even theoretically, the solution is better if it is actually more concise, and the reason is you're creating less problems in terms of issues. So in here, they try to achieve the same code while avoiding this kind of back and forth by setting the value all the time within a free loop. And they were just doing multiple tests under assumption that the left-hand side of the end within the while is going to be tested before the run part. That is actually the assumption. So I provide another variable, but I'm actually removing additional flags. So the variable last actually recalls which of the thread previously wanted to access the critical section. So that is going to act similarly to turn, basically. But I'm testing now for the turn within the while condition, basically. So within the lock, in here, the thing that we're doing is that the thread will wait while the other wants to enter. So the thing that will happen is that I'm setting myself to true and I'm checking whether the other thread is also allowed to want to access the critical section. So the thing that will happen is that if you have like the resolution of a contention by just adding last equals to I, basically, and that is actually the way to solve the contention in Peterson. And definitely the thing that happens, so let's suppose that you have description, so everyone is set to true, and someone set to the variable to last to something, so either that will become 0 or 1. So the first part of the condition will be true for all the processes, but the last part will be different for one of those, and for the process for which the last condition is false, then they're going to be allowed to go inside the critical section. The other one will wait indefinitely up until the left-hand side will be false again, and that is actually done only when the thread will run the unlock. So as you see in here, I'm always assuming like the liveness condition of the program. So I'm always assuming that the thread will quit eventually from the unlock, and we'll call it unlock, so they will quit the critical section and move to exclusion. Otherwise, the code will be never correct, but then the issue is not the code itself, it's the logic of the threads using the protocol. So it's not a problem of the protocol if you're using your logic methods correct or the wrong way. So that's why you have like always in this kind of theoretical contraptions to have like liveness assumption. So if something is meant to be good, then also the program is good. If something bad happens, then already something bad happened. So it's more real that you could make something work if some other preconditions are wrong. So that's why having like proper theoretical assumptions is required. So therefore, only if I'm not the last one, I'm allowed to enter that. And definitely this kind of code is also working if everyone is going to access one at a time. So if I'm setting myself to accessing that, then I will basically be I'm the last one accessing the critical section, but definitely another thread was not accessing the critical section, so I could go inside nevertheless. So even though, so that works even though all the threads are scheduled one at a time. So in here, basically we're doing a proof by induction. So we're considering the three cases, and that is actually how to do that in a more precise way. So either tries one process tries to enter the critical section and the other one is not in the critical section, and therefore that is actually the thing that we covered last now, so you can immediately enter. In the second case, one tries to enter the critical section and the other one is already in the critical section. So in the other one, then I'm the last, and another one is actually in the critical section, so I'm continuously waiting. And in the third case is actually the thing that we covered first. So in here is suppose that T1 and T2 are trying to enter the critical section at the same time. So everyone will have the variable for themselves set to true. And then it will be very dependent on who is setting the last operation last to know actually who entered or wants to enter the critical section last. And given that we're assuming interlock, so we have always like volatile variables, then we're always seeing the last value, and we know that we cannot interfere between each other. So definitely, this is actually the thing that was